Hello everyone, and welcome to this video on maximally symmetric spaces and the Riemann tensor. Now, a viewer of this channel requested this video, pointed out he disagreed with the other video version of it that runs under this title, so I'm going to make it more in line with what perhaps might be a better argument for deriving the Riemann tensor for maximally symmetric spaces. So anyway, in short, this video investigates the idea of a maximally symmetric manifold or space and derives the Riemann equation for this space using the metric tensor and Ricci scalar. It also shows how these spaces must have a constant Ricci curvature scalar. So let's make a start. So the point of this video is for a maximally symmetric n-dimensional manifold or space, we want to find the form of the Riemann tensor. This here, what is it? Okay, and we want to use some arguments. So let's make a start. All right, so space is homogeneous. Maybe I might, can that fit in there? No, it's going to be a nuisance, so I'll get rid of it. All right, now a space is homogeneous if it is invariant under any translation along any of its coordinate axes. Think of Minkowski space. A space is isotropic if it is invariant under a rotation of any coordinate axis into any other coordinate axis. I mean, you can swap x and z. What's the difference in Minkowski or Euclidean space? It just depends on what coordinate system you want, but you can swap one into the other, rotate one into the other. In an n-dimensional space, there are n coordinate axes, and so there are n number of translational isometries if the space is maximally symmetric. In this same space, there are n number of coordinate axes that can be rotated into n-1 other axes. However, we don't count a rotation of, say, the x-axis into the y-axis as being different to a rotation of the y-axis into the x-axis. So we just count it once. All right, so the total number of distinct rotations is n times n-1 on 2. And for a maximally symmetric space, we can expect the following number of isometries, n number of translations, this number of rotations to give you a total number of, if you do the algebra, n times n+1 on 2. So for example, in the 4 dimensions of Minkowski spacetime, there are 10 Killing vectors made up of 4 translational isometries, and 6 rotations, 3 of which are boosts and 3 of which are pure rotations. So Minkowski spacetime is maximally symmetric, and there's a couple of videos on that, on how the Killing vectors were arrived at. So have a look in that area there. There's about 3 dealing with the Killing equation. Now, an n-dimensional manifold M is maximally symmetric if it has n times n+1 on 2 independent Killing vectors. Now remember, a Killing vector field, and I'm just expressing here the coordinate component here, k alpha, we'll take that representing our vector, is a Killing vector if and only if it satisfies the Killing equation here. And there are videos on this. So I'm just reminding everyone. Now, another thing is the Lie derivative of the metric along a Killing vector vanishes. All right? So the Lie derivative of the Killing vector in the direction of the metric is 0. Okay, the metric doesn't change moving in the direction of the Killing vector. Right, the Riemann tensor transforms covariantly. All of this is for maximally symmetric spaces. The Riemann tensor transforms covariantly under diffeomorphisms, where diffeomorphisms are invertible functions that map one differentiable manifold to another. Covariantly means keeps the same form under different coordinate systems. And in particular, its Lie derivative along any Killing vector vanishes. So the Lie derivative of the Killing vector in the direction of the Riemann tensor is 0 for every Killing vector, k alpha. All right? Because an isometry is a length-preserving map, meaning it moves an object without changing its size or shape, maps curvature tensors to themselves. Okay, the main types of isometries are translations, rotations, and reflections. Now, at any point P, these Killing vectors generate all possible infinitesimal rotations and translations of the local tangent space. So each point on a manifold has its own tangent space. and that's what we mean by the local tangent space. And so at any point P, these killing vectors generate all possible infinitesimal rotations and translations. The subgroup of isometries that fixes P, so P fixed, acts as the full orthogonal group, ON in dimensions, or the special orthogonal group, the rotational groups of order N, if orientation preserving on the tangent space to the manifold. So the tangent space of manifold at point P, manifold M. Hence, any tensor field evaluated at P that is invariant under all isometries fixing P, so fix a point in your manifold and consider rotations around it, must also be invariant under all rotations of the local orthonormal frame. All right? So the local orthonormal coordinate system. At a given point P, if all directions are equivalent, because the orthogonal group ON symmetry rotates them into one another, then any invariant quantity must, so if all directions are equivalent, because of the symmetry of the manifold about that point P, then any invariant quantity must have no preferred direction, okay, and depend only on quantities that remain the same under rotation. So namely the metric, G, mu, and U, which measures lengths and angles, and possibly the orientation symbol, Levi-Civita symbol, this one. Right, tensors invariant under all rotations must be built from these two building blocks, okay? So let's remind ourselves of the symmetry properties of the Riemann tensor. So we have this anti-symmetry in the first pair, sigma, rho sigma, okay? Gives us the negative of the Riemann tensor when we swap those first two indices. Anti-symmetric in the second pair. All right, so if you have a look here, mu nu to nu mu. Symmetry under pair exchange. So if we take rho sigma, that first pair, and the second pair mu nu, and we swap them about, it's symmetric under that change. And then very helpful for today's work is the Bianchi identity, the first Bianchi identity, and that's this one. And well, that's going to help us in working out the form of this, as you'll see with the indices, working out the form of the indices in this expression for a maximally symmetric space. So what we need, as I pointed out on slide 2 here, we need a rank 4 tensor constructed only from the metric that has the same symmetries as these. All right. So let's start with something like this first one here. Rho sigma mu nu proportional to this object here. So compare indices with those of the Bianchi identity above. In other words, where did I get this from and this? Okay, and if you notice closely, rho mu sigma nu, rho mu sigma nu, okay, and this here, the indices rho nu sigma mu, so rho nu sigma mu, okay, we have got, we've got this term here, which is this one, and then this one looks like this one. Sorry, looks like this one. Sorry, that one. And this one looks like this one. So that's a bit of a hint, and we'll see that that is actually relevant. So now impose the required symmetry step by step. So the anti-symmetry in rho sigma is that. So let's start here with our proposed form of the Riemann tensor for a maximally symmetric n-dimensional space, manifold, and put the minus here in front of these. Okay, and we notice then that this left-hand side is equal to this if we set A equal minus B. So that would be A, and this would be minus B. So that's suggesting something of the form, this here is proportional to this. Okay, that's what it's suggesting there. You'll notice these indices will match up with the Bianchi identity there. allowing for symmetries within them. So rho mu interchanged is the same as the metric with indices mu rho, okay, assuming there's no torsion on the manifold. Now, let's have a look here. Anti-symmetry and mu nu. The above expression automatically has that symmetry as well, as I was just pointing out. You can swap these two here and you still have the symmetry applies. Okay, that'll make the right hand side negative of the left. Exchange symmetry, we can interchange these. Is symmetric under this exchange, you can do that. So it also satisfies the pair symmetry. The Bianchi identity, the combination satisfies the Bianchi identity, and that's what I was getting at before. Okay, we'll see a bit more of that in a moment. All right, so here's the Bianchi identity again. All right, this form here is these two terms, and then this one here was this one, and this one here was this last one. Now, using symmetry, noting things like with the metric there, you can swap the indices and it's symmetric. Okay, so they're equal to each other. We see that pairs 1 and 4 cancel. So this one. Remember, the Bianchi identity means you sum these and you get 0. So in our proposed form for the Riemann tensor, then if it's going to be this one is going to be this one, and this one's going to be this one, then we want it all to sum to 0. We want it to obey, must obey the Bianchi identity. So if you have a look at pairs 1 and 4, okay, you notice that they're going to cancel. So rho mu and mu rho are the same thing. Sigma nu, and so this cancels with this one. And then we'll find the same thing happens with pairs 2 and 5. Rho nu, sigma mu, mu sigma, they're the same. So this one cancels that one out. And then with 3 and 6, we have sigma rho, rho sigma. So those two metric terms there are the same. Mu nu. So this one cancels this one out and we get 0, and the Bianchi identity holds. So the form of this maximally symmetric Riemann tensor for this maximally symmetric space is starting to hold up thanks to the Bianchi identity and other symmetries. So the Bianchi identity holds for our proposed rank 4 tensor, which is this object here. Okay, the Bianchi identity holds for this, as you can see here and here. And all that summing to 0. Hence, this is the unique metric built object with the Riemann symmetries. Remember, we got this negative from that before, A was minus B. Now, any two rank 4 tensors with Riemann symmetries that are invariant under all rotations must be proportional. And whichever way you look in this space, there's no preferred direction. They're all the same. Okay, all that differs when you rotate from one to another is just a factor. So they must be proportional to each other. We need something of the form this, and so here's our factor of proportionality, Q, for some scalar Q. Let's see if we can find out a little bit more about this scalar. The proportionality constant can depend only on scalars invariant under all isometries. So, i.e. the Ricci scalar R, which is constant on a maximally symmetric manifold. So think of the 2-sphere of radius A with Ricci scalar R is 2 on A squared. Right? So by maximal symmetry and isotropy at any point P, right, isotropy I should say, not isotropy, isotropy, that's the same in all directions. However, you say at point P, turn around and rotate and turn yourself upside down, whatever, but all directions look the same. We must have this evaluated at point P, must be this evaluated at point P. Some scalar Q, which may a priori depend on the point. But the lead derivative of the Riemann along all killing vectors vanishes. Okay? There's no, okay? The curvature is the same everywhere. Just think of yourself on the 2-sphere, whatever direction you look at, the curvature is the same. up, down, left, right, however you look, the curvature is the same. Okay, hence the Ricci scale is that 218 squared. Okay, but so the lead derivative of the Riemann along all Killing vectors vanishes, and the manifold is connected, so Q is constant on M. So globally, this holds. This is the key structural result from Killing isometry arguments. But we're going to go further and find out what this Q is. All right, so we'll now determine Q in terms of the Ricci scalar R. So we start with our expression here, and we calculate the Ricci tensor. Well, the Ricci tensor is two indices, so we need to contract. So we're going to raise an index, and then we're going to contract. So we'll raise the rho and the mu here, and then contract on those two. So we get this object here, raising out, which multiply through here, leave Q there outside untouched. Okay, so we're just multiplying the inverse metric G rho mu across this. Okay. Now let's have a look at some things here. Well, G rho mu, upper indices, lower indices. Well, when that's summed out, we just get M, the degree of the space, the degree of the manifold. Okay. Then next term here, if we have a look here, we've got here the Kronecker delta will apply. Did I do that? Oh no, hang on. I've still got to deal with this bit here, haven't I? Okay, so second line down. So we've got this here, that's N. So this metric component here, G sigma nu, multiplying that across. So this is N from this line here, N. So we get N times this object. Okay, that's as far as we'll take that one. Now we have a look at what's happening over here. And this is where the Kronecker delta comes in. So inverse metric G rho mu, G rho mu. Okay, so the Kronecker delta applies those two, where mu, see, summing out the rho, mu here, so the Kronecker delta applies, G sigma mu. Now, when mu is equal to nu, right, this, because you've got one index up, one index down, that sums out, you get G sigma mu, okay? Similar to that. Okay, so the Ricci tensor, R sigma nu, is Q times this object here, because remember all of this now is just N times G sigma nu. And this one here just becomes, second term, it just becomes G sigma nu. Notice that we're going to take out the common factor of G sigma nu. And we're left with the N factor of N minus 1 here times this unknown Q. And so the Ricci tensor then is just R sigma nu is this object here, scalar Q, whatever that is, times this factor of N minus 1. N is the dimension of the space times the metric here. So let's keep going. Now, so this is what we found, the Ricci tensor. Now take the trace to get the scalar curvature R. Okay, so again we use the inverse metric here like that. This will give us R here. Both indices sum out. So we get this object here times that, Well, pull out this factor, the scalar Q and this scalar N minus 1 here, pull that out front, and we've got this like that, which as we've seen before, is just N the dimension. When we sum that, it's just N the dimension of the space or manifold. So we get Q times N minus 1 times N. So the Ricci or scalar curvature, Ricci scalar or scalar curvature R is this object here. Okay, and we can rearrange to give us Q is R on N times N minus 1. And as we've seen with the two-sphere, this Ricci scalar is constant. Okay, and so let's substitute this back in here. So remember, this is the object we before. The only thing we need to find now is the Q. So substituting it back in, finally we found that a maximally symmetric n-dimensional manifold of space has a Riemann tensor given by this, where R is constant. Okay. All right, next bit. So just to summarize here a bit. Now the key input from Killing vectors maximal symmetry was that the full isometry group acts transitively and isotropically. So invariance under all these isometries forces the Riemann tensor, invariance under all these isometries forces the Riemann tensor at a point to be an orthogonal degree n invariant 0,4 tensor with the usual Riemann symmetries. So by representation theory, it must be proportional to this. Okay, where we represent these symmetries as these matrix-like objects here. All right. So the Bianchi identity was hugely important in finding this, and that gave us the form of the indices, if you remember. So just remember that's how we looked at the Bianchi identity, and we found that when we look at the arrangement of the indices, we had, I'll go back, we had R sigma mu nu, first element of the Bianchi identity, then rho mu sigma nu, the second, rho nu sigma mu, the third one, third combination of elements for the Riemann tensor, and those three added together gave us 0. That was the Bianchi identity, and these indices just follow that Bianchi identity. All right, now the vanishing Lie derivative, so the Lie derivative of the metric in the direction of the killing vector, each and all killing vectors for all killing fields, ensures that the proportionality constant is the same at all points, connected manifold, so Q is constant. Then contracting yields the relation between Q and the Ricci scalar R. All right, thank you very much everyone for watching this video. I hope to see you all in the next video. Take care of yourselves, and I look forward to hearing your comments. I hope you find this useful. If you do, please like the video and please subscribe. I greatly appreciate that, and I look forward to seeing you next video. All right, wherever you are in the world, take care. Good luck to you, and I look forward to seeing you again. All right, bye everyone.